All right, this is a small addendum onto our lesson about Bernoulli's. I wanted to finish up with one other thing that is commonly brought up in relation to Bernoulli's and was actually a predecessor to it. Torricelli's law, or Torricelli's theorem, I've heard it several ways, I can't remember which exactly, but talks about an application that was later a subset of Bernoulli's equation, related to what we had seen there. But in short, Torricelli's theorem, and this is one that is common to a lot of AP or introductory physics questions in fluids, where you would have a container that is filled with water, and you would make a small hole right down, say, here. And that allows, based on the water pressure, for water to go shooting out and then fall down, basically. So we end up with effectively a small water spout or a small water gun. The idea on this, in a brief summary, was Torricelli said that the water depth, h, would have a direct effect on how fast the water speed is as it came out of the hole in the container. Now, for this to happen, you need a relatively small hole, comparatively, because if you just do a huge gash, it would come out, but the idea on this is a small rigid hole for Torricelli. Now, I'm not going to go into all the details on that. He found that there was a ratio relating it where you end up with, you could almost draw a line at 45 degrees down. I'm not going to go into the ins and outs on that, mainly because if you're solving for that sort of thing or a question related to Torricelli, use what we introduced in the Bernoulli's equation, and it gives you a more robust answer, because then you could have a pressurized container up here where the ambient pressure here is not the ambient pressure here. So Torricelli's is a simplified version of the Bernoulli's equation. But I want to emphasize that Torricelli, I think, was in the 1600s, and Bernoulli's equation came significantly later. So it was actually, Torricelli's was one of the ideas that people had found that later got combined into a more complex and more, not universally, but a more robust application. It's a lot like Charles's law and Boyle's law and Avogadro's law, that were all individual bits of science that were great in their own turn, but then got combined into what we now call the ideal gas law, for those of you familiar with it. In short, the way that this is normally described as is that the launch speed, or the flow speed down here, is equal to the square root of 2gh, which is what you would get, hopefully that looks somewhat familiar from energy conservation, but you can go through and you could apply, if we have the same ambient pressure here and here, say atmospheric pressure, then those would end up canceling out, and we're basically turning the hydrostatic pressure into dynamic pressure at this point. Or we're turning gravitational potential energy into kinetic energy, which was the original phrasing for Torricelli's theorem. So while this is applicable and maybe something I don't recommend you all simply memorize things, but I have seen quite a few questions related to this, including on the new CED and the example things that College Board has released. So I wanted to talk specifically about that. And then the other thing that I've got is hopefully a demonstration of it. So what I've got is, all right, so we had a small issue with that. Turns out my demo worked just fine, except I forgot a couple things. One, to remove the cap, so make certain that you do that, because I had it stored for a while. And two, I'd forgotten that I made it a couple of weeks ago when I got lazy and I didn't actually drain all the water from it, and that these thumbtacks are actually made out of ferrous metal, and therefore they rusted and caused problems. I also double-checked the view on the camera, and I'm not certain that the fluid stream was coming through as well as I'd like, so hopefully this is going to show okay. But I set this back up with one of the spare ones. We've got a water jug here, and now I've put in a variety of thumbtacks at different locations. So I'm going to pull out the one up top. We can see that it comes out about like this. So my finger's going down like that. I'm going to pin this back in. We got this one. We've got it coming out farther like that. We got this one coming out even farther. This one going almost to the far side of this little bucket, and then this one going a similar distance there. Okay, so hopefully you're able to see some of those. I'll double check in just a moment, but I'm going to pull all of these thumbtacks out so we can see the different streams. The top one here is not coming out near as far because it has a lower velocity, and then we've got these going like this. The ones towards the bottom are going farther out. Now, Torricelli had it where you would have basically something where this should ideally come out to about a 45-degree angle, and that was one of the things that Torricelli actually set up in the specific theorem. That being said, Bernoulli's equation actually allows us to work with this. Now, as this drains down, the speed is going to start dropping off for the different ones because our water level is going down, and therefore their functional height, their depth, is decreasing. So that's what we've got for Torricelli's theorem. Okay, I'm going to try and pin these back up, and then when I'm done with this, I'm going to drain all of it so that it doesn't end up. All right, so I've set this up. Hopefully we get a little bit better contrast. We have our container. I need to remember to take the lid off. I was about to make that same mistake yet again because I need the thing open to atmospheric pressure. If I leave it sealed, as it begins to drain, it actually offsets the pressure there. But we're going to go through, and I'm going to try and remove each of these so that we can see. Now they are going to start tapering off because the flow rate is enough to actually have it narrow down, but hopefully we are able to see this pretty well. And we have Torricelli's theorem. All right.